All right, we're good to go. All right, guys, so we're kind of on this journey of second order differential equations, right? So if you remember where we started, we're basically started with linear. Let's see, we started with homogeneous, which is linear, right? It's linear where the right side is zero. They're second order. We had constant coefficients, and that's where we started. And we used the methods of 4.2 and 4.3, the auxiliary method, basically, to solve those. Okay. So now what we've been doing is we're trying to basically relax the restrictions that we put on our initial restrictions. So what we said is like in 4.4 and 4.5, this is finally after when we're dealing with non-homogeneous equations. Basically, as long as the non-homogeneity was suitable, then we can use, it's called, remember the method of undetermined coefficients? Okay, the method of undetermined coefficients was discussed in 4.4, and we discussed a direct approach. Undetermined coefficients finds one particular solution to the differential equation. Okay. Now in 4.5, we continued to discuss undetermined coefficients, but we kind of coupled it with the superposition principle, which allowed us to work with more non-homogeneities. In 4.4, we worked with non-homogeneities that were polynomials times exponentials times sine or cosine functions. And then in 4.5, we basically allowed ourselves to extend that to include linear combinations of those functions using the superposition principle. This is where we use solutions as building blocks to build more complicated equations that have a linear combination of those non-homogeneities. Okay, but that's still very limiting because we're still stuck with only, combinations of these guys. So there's lots of other functions that don't fall into those categories. And so what do you do when you have a non-homogeneity f of t that is not suitable? What do you do? Well, in those cases, we're going to use this kind of all-inclusive method. This method actually works 100% of the time. It's called variation of parameters. And you might wonder, well, if it works 100% of the time, why did we waste our time doing undetermined coefficients? Right? That should be your question. Well, the reason is because undetermined coefficients is generally a lot easier. The drawback is that it only applies to suitable non-homogeneities. So as a general rule, what you want to do is use undetermined coefficients when you can. But if you have a situation where you have to use variation of parameters, you have it available to you. If it's not suitable or it's not a linear combination of suitables, then you're going to have to use variation of parameters. Okay, so there's another advantage to variation of parameters. It turns out that you can also use it in a kind of a super relaxed situation where you have non-constant coefficients. And what I mean is variable coefficients. So now we're relaxing the conditions even further. And I'll show you how to do that. Actually, here's an example down at the bottom. This is a variable coefficient equation. All right, so what do I mean by variable? Well, look at the coefficients in front of the y double prime, in front of the y prime, and in front of the y. Do you notice all of them are functions of t? So that means that they can vary. So if you remember before, we didn't have a t there, and we didn't have a t there, and we didn't have a t there. And the reason why is because they didn't vary. So there's no reason to write in a1 of t, a2 of t, or a naught of t. Okay, so we can use variation of parameters on those situations too.
Professor?
All right, so yeah.
I have a quick question. Will these methods that we're learning for the more relaxed, aka the variable coefficients, will these work for fixed, or is it specific to every case?
Oh yeah, the variation of parameters method.
Yeah.
Yeah, it'll even work when they're constants. So
Okay.
Yeah, so that's the first, I mean, that's the bulk of this section. The only reason I mentioned variable coefficients is because we're going to talk about it in the next section, and it happens to work. There is one issue that we do have to talk about, which we'll discuss at the end of class. These are actually a lot harder. When you have variable coefficients, it's a lot harder. So, but we'll get there. We actually, in general, are going to have to use series to do this. Do you guys remember series from Calc 2? Yeah, they're back, right? So, we'll get to that in chapter 8, but we can still say something now about these types. So, this is kind of a one-off. I'm going to just talk about at the end. Okay. So, first let's talk about what this method is, how we're going to construct it up. So I like to use the word motivation. It's basically the theory on how we're going to set this method up. So let's say that we have a non-homogeneous second order linear equation like so. You'll notice the coefficients are constant in this case. That's going to be the bulk of the questions in this section. And then you have this non-homogeneity over there, f of t. So of course the constants, the first constant can't be 0, otherwise it's not a second order. And then you just use first order methods. So let's see. Well, we can use the auxiliary method from 4.2 and 4.3 to find the general solution to the corresponding homogeneous equation. This is section 4.2 and 4.3. We can do this 100% of the time. We have a complete theory. So all you have to do is follow that procedure and you'll get two linearly independent solutions, y1 and y2, and then you just slap constants in front of them. And then you have the homogeneous solution to the corresponding homogeneous equation. It's called YH, right? All right, but if we're trying to solve this guy, if we're trying to find the general solution to this guy, we're also going to need a particular solution to this guy. We have the homogeneous to the we have the solution to the corresponding homogeneous, but we just need one particular here. So this is where it gets more interesting, right? So if f of t happens to be suitable for undetermined coefficients, which may or may not employ using the superposition principle, then we can find yp using undetermined coefficients. Okay, now, do you remember what undetermined coefficients, how that works? Do you notice there's no real integration with undetermined coefficients, right? You take a stab at the form, and then we have some complications, right? You take a stab at the form, and then you take the couple derivatives, you plug them in, and then you equate coefficients on both sides. Remember that? Okay. And so once you find that, then you just add these two together, and then you have y, which is a general solution to this guy. The problem is, what if that f of t is not suitable? What if you can't use undetermined coefficients and the superposition principle doesn't help? Well, like I said earlier, we're going to use variation of parameters. So here's the idea. The idea is that we're going to kind of use the equating coefficients, choosing a form technique that we've used with undetermined coefficients, but it's a little more complicated. We're going to find a particular solution of this form. Okay, so I'm kind of picking it out of thin air, although not quite. It's not unreasonable to think that there might be a particular solution of this form. In fact, if we go back to the homogeneous solution, it kind of looks like the homogeneous solution, right? You can see the difference, right? Instead of the C1 here, we have a variable function V1. Okay, and instead of the C2, we have a variable function V2. Okay, and then we have our known solutions to the homogeneous equation right there. So our goal basically is to use this form and basically figure out what V1 and V2 have to be in order to be solutions. And the way we've done that in the past is by equating coefficients. All right. The reason we call this method variation of parameters is because basically we have parameters up here, but now we're letting those parameters vary. So it's called a variation of parameters method. All right, so how would we do this? Well, we have the form. This is the form we want to use. So we're going to use kind of the same technique we used before. We'd like to find the first few derivatives and plug them in and then equate coefficients and solve for them. So let's take the first few derivatives. So here's the 0th derivative. I'm differentiating this guy, right? So that's the 0th derivative. You'll notice that I'm dropping off the function notation. The reason for that is this is getting pretty messy and it's just too much to write out and it gets confusing with all the symbols. So once you start working with the V1s and V2s, I would suggest dropping the function notation. It's still there, we just don't write it. All right, so there's the 0th derivative. Here's the first derivative. So in order to do this, both of these are functions of t. So we have to use the product rule on this guy. So right, first d second plus second d first, or vice versa, doesn't matter. So that's going to yield this guy. And then we have to use the product rule on this, and that yields that guy. Is that part okay? Okay. All right, well, we also need the second derivative, right? Because we have to plug all these in. So, but then the thing is like, this is getting really ugly. This is going to take 2 terms. That's going to take 2 terms. And we're going to have second derivative. It's going to get really ugly. So it would be super nice if there was maybe another way that we could do this, because I really don't want to expand this out and equate coefficients. And there is. So here's the trick. And this is not obvious, but it hopefully will become obvious once you see it. We have 2 functions defined, V1 and V2. Since we have 2 functions defined, we basically have 2 degrees of freedom to play with. So I'm going to go back and show you something from algebra that you maybe never thought about. Can I do it here? I'll do it down here. All right, let's say we have, there we go, 10. Let's say we have the equation 2x plus 3y equals 13. All right, so how many variables do you see up there? You have 2 variables, just like our problem. We had two variables, V1 and V2 to find, right? Now, if I asked you to find a solution to this, do you think you could? Can you give me an ordered pair that works? X equals what? Tina says 5. Why don't we do this? We'll write it as an ordered pair. 5 for the X and 1 for the Y. Is that okay? All right, well, that's a solution, right? So if all it was after was a solution, that would be fine, right? There's other solutions though, right? What's another solution? You can let me know over there in the chat. Yep. 2, 3, okay. All right, what else? 8, -1. Okay. But do you guys see there's going to be an infinite number of possible solutions here? In fact, if you graph this, it would be a line basically, right? And then anything on that line, any ordered pair on that line would be a solution clearly, right? Okay, well, let's think about this. Since let's say I only want one solution. Well, since I only want one solution, I don't need all of those. What I could do is I could add an extra restriction. Right now I have one restriction. I know that the relationship between X and Y has to be such that 2x plus 3y equals 13. But what if I did this? What if I also required that X plus Y equals 5? So if I add this extra restriction, can I still find a solution?
Yeah.
Yeah, it would just be that one right there. I would lose all the other ones, right? Not that one. I'm sorry, this one right here, right? It would be that one right there because the two lines would intersect at one point. Okay, so what's the point of all this? Well, the point of all this is that we have two variables, a V1 and a V2. And all I need is a pair of solutions that works for the equation once I plug it in. So if I wanted to, if it made the work easier, what I could do is add an extra restriction. The only reason to do that would be to make the work easier, of course. But you're free to do that because there's two variables and all I need is a pair that works. So that's exactly what we're going to do here. So here's how this works. You notice right here in the first derivative, you see this guy? It sure would be nice if that was 0, right? Because then it would drop out and then this would be our first derivative. And then I could just differentiate that guy and that would make the work a lot easier. So what I'm going to do is I'm going to add an extra restriction since we have 2 degrees of freedom and I've only so far, have one requirement. Let's add an extra requirement. All we need is a pair that works. So let's ensure that this is equal to 0. That's going to be one of our requirements. Now it turns out this always works. They're not parallel. They will intersect at one point. So you can be assured that it will work. So here's what we're going to do. Now that we have this extra requirement, it's greatly simplifies our work. So now we can take our list and now we can finish it off knowing that this is now 0. The first derivative is now much easier, which means the second derivative is simpler. Instead of 8 terms, there's only 4 terms. Are you guys following? Okay, well, we're going to plug this in to the differential equation to get the, because it has to satisfy it. That's one of the restrictions. So here's the original differential equation. Okay, so we're going to plug all the derivatives in. So there's y prime, y double prime, I should say. There is y prime, and there is y. All right, now what we're going to do is we're going to move this around just a little bit. You see these 2 terms right here in blue? We're going to pull those out the front along with the A, and then we're going to distribute the A and reorganize everything, rearrange everything, massage the algebra. We're going to put all the y1 terms in the same expression and all the y2 terms in the same expression. Just a little algebra. The next thing we're going to do is just make a simple note to ourselves. Y1 and Y2, if you remember what those are, where are they? Where's my Y1 and my Y2? Yeah, here they are. Oh, yeah, the Y1 and the Y2, although here they are. The Y1 and the Y2 are basically the 2 linearly independent solutions we found to the homogeneous equation. Okay, so we're going to use those. We already have them available. And so those are used right in here. And so what do we know? Well, we already know Y1 is a solution to the homogeneous. So that means if I take Y1 and I plug it into the left side of the homogeneous, that is the left side of the homogeneous equation, then it has to equal 0 because it is a solution. We know the same is true for Y2. Y2 is also a solution to the homogeneous equation. So this whole term zeroes out, this whole term zeroes out. And what we're left with is this requirement right here. If we divide both sides by A, then we have this requirement. So now we have our 2 requirements, right? This was our arbitrary requirement to simplify our work. And this is the requirement that came from plugging in the derivatives into the differential equation. All right, so we have 2 variables. We have a V1 prime and a V2 prime. V1 prime and a V2 prime. The Y1 and the Y2 are known. Those were given at the very beginning. Those were the solutions, linearly independent solutions to the homogeneous equation. So here's what we're going to do. We've got 2 variables and 2 equations. Here's the 2 variables. It's weird that your variables are derivatives, but it still works. We're going to solve for V1 prime and V2 prime. Once we solve for v1 prime and v2 prime, we can integrate each of them by direct integration to solve for v1 and v2. Once we solve for v1 and v2, we know the form, so we simply plug in the v1 there and plug in the v2 there. And this will be a particular solution to the original differential equation. All right. We don't really have to worry about constants here because constants are going to get absorbed. So I'll show you that when it happens. But let's jump in, use the method. Let's restate the method, simplified. So this is the summary of the method. So let's say you want to determine a particular solution to this differential equation, and there's no restrictions on f. Well, first thing you want to do is find two linearly independent solutions to the corresponding homogeneous equation. You guys can do that using the methods of sections 4.2 and 4.3. Basically, you're finding YH. And then after that, you're going to set up this system. That's the system we derived in the motivation section above. Okay, so you'll notice that this system relies on Y1, which you found in step 1, and Y2. So we have those. You're going to have to find the derivatives of Y1 and Y2, which you guys can easily do. You have a 0 on the right side up here. Up top here, you have an F. You have F, it's given. And you have an A down here. And that's given too. That's the coefficient of the second derivative term. All right, and then you have your variables, v1 prime and v2 prime. And those are going to be placed here, here, there, and there. Now, although it looks super complicated, really this is just a system of differential equations, which you can solve for. You can solve for v1 prime and v2 prime. It's just simple algebra. There's no calculus required. Once you find v1 prime and you find v2 prime, you're going to integrate both using direct integration. And then what you're going to do is choose convenient constants. Doesn't really matter what you choose because it's going to get absorbed anyway. So, you know, usually you're going to choose a c equals 0 if that's the particular problem you're working at, or maybe a c equals 1, depending on what's easiest. And then you'll have your particular solution, YP. Okay, that's the rule. That's the method. Now, the method is not for finding a general solution. It's for finding a particular solution. But you guys know how to find a general solution. You need YP, and what else do you need?
YH, right?
You need YH too. But you've pretty much done most of the work in part 1, right? Pretty much did the work to find YH. To find YH, you did take C1, Y1 plus C2, Y2. And there you have YH. Okay, so here we go. Let's try it. We're going to find a general solution to this second order linear differential equation. The solution that we're looking for should be valid on negative pi over 2 to pi over 2. So first of all, you should always try to use undetermined coefficients if you can. It's much easier in general than variation of parameters. So what you want to do is take a look at the non-homogeneity and then ask yourself, can I use undetermined coefficients on this? What do you think? No, undetermined coefficients only works on polynomials, exponentials, sines, and cosines, right? Or products of those, or linear combinations using the superposition principle. So unfortunately, we can't use undetermined coefficients. So all we have available to us right now is variation of parameters. So you always start off with the homogeneous case because we're going to need the Y1 and Y2. So let's see. We'll write down the corresponding homogeneous equation. There it is. We'll set up the auxiliary equation and we'll solve it. R equals I and R equals negative I. So by the auxiliary method, the general solution to the homogeneous equation is right there. We're going to need YH, right? Because we're finding the general. Okay, so there's YH. All right, notice that in our method, we've basically created two linearly independent solutions. We're going to need these guys. These are used in variation of parameters, so we'll hold on to those. All right, so finally, we're going to need YP. So YP is going to be applied in this situation. I'm sorry, variation of parameters because it's a tangent function. So we're going to set up our system. So you just copy down this form for your system. As far as the values for the different parameters here, the f function in this case is tangent t. So that goes up top. Your coefficient is a, which in this case is 1. It's just the coefficient in front here. It's 1. Let's see. We're going to need the y1 and the y2. We found those in the auxiliary case, so cosine t and sine t. We're going to need their derivatives, so that's a quick calculation. And then we plug them in. Okay, so that's the system you're trying to solve. Remember, you're trying to solve for v1 prime and v2 prime. Those are the variables we have. All right, so we're going to use kind of standard algebra techniques in order to solve this system. What you want to do is probably use the elimination method. And then once you find a solution, you could back substitute in to find the other variable. Or what you could do is just use the elimination method again and eliminate the other variable. So depends how you want to do it. All right, so let's start off by eliminating the v1 prime. Right, so you ask yourself, how could you eliminate the v1 primes here? Well, what you'd want is you want these terms to have opposite sign. So what I'm going to do is I'm going to take the top equation and we're going to multiply by sine t to every term. So if I multiply the top equation by sine t, I'll get that equation. Is that okay? All right, for the second equation, I want something that's opposite. So I'm going to take the bottom equation. And since that negative is already there, I can simply multiply the entire equation by cosine t. Is that okay? Do you notice that these guys, oops, are opposites? Like if I added this guy to this guy, the v1 primes would disappear. They'd get killed. Do you see that? Okay, so that's what we're going to do. This is the standard elimination method from algebra. So we're just going to add the equations together, and we're going to eliminate v1 prime, and then we'll just have an equation in v2 prime, which we can solve. So when we add the equations together, the v1 primes cancel, and what we're left here is a sine squared t v2 prime and a cosine squared v2 prime. And on the right, we have 0 plus cosine t tan t. Like so. We can factor out a v2 prime, and then cosine squared plus sine squared is 1. And by the way, cosine t times tan t is sine t. So we've solved for v2 prime. Okay. Now, the next step is going to be to integrate, but we're actually going to hold off on that. I like to find my variables first. So let's go ahead and let's solve for v1 prime, and then we'll go and we'll integrate both of them. So v1 prime, how do you find v1 prime? Well, if you want to find v1 prime, you could use this and back substitute to solve for v1 prime, or you could just use the elimination method again. So if I wanted to take my system and eliminate the v2 primes, I'd probably take the first equation and multiply maybe by cosine t and the second equation by negative sine t, and then add them together. That would eliminate the v2 primes. And then we can solve for v1 prime. There's your v1 prime. All right, so I'm not going to go through the specifics there. All right, now that we've got v2 prime, we've got v1 prime, we're just going to integrate each of them. This one's easier, so let's start with that one. If you integrate equation 19 on both sides, you're going to get the integral of sine t dt, which is negative cosine t plus c1. You don't have to worry about the constants. They're going to be absorbed anyway. So just keep note, we only care about that cosine t, that negative cosine t. As far as finding v1, we're going to integrate this equation 20. So if you integrate 20, you're going to integrate negative sine t tan t. So this is probably where you want to brush up on your integration skills a little bit. This is not an obvious one how to do. There's no nice substitution to use, but what we can do is employ, let's see, we can employ a trig identity on the top. We can break it apart, break the rational expression down into two rational expressions. We can push the negative inside, which inverts them or reverses their order. And then finally, we're down something that seems reasonable. I think we can integrate cosine t. That one's pretty straightforward. That's just sine t. This one over here, you probably remember doing at some point in Calc 2, right? The integral of secant t. Yeah, you did this at some point. So I'm not going to review how to do it. I'd like you guys to do it yourself, but I'll give you a hint. It's not obvious. What you're going to do to integrate secant t is you're going to multiply the numerator and denominator of secant t by secant t plus tan t. And then hopefully you'll see how it falls out. So do that one on your own just for practice, because you never know. I could have something like that on a test at the end of the semester. All right. So again, we don't really care about the constant. So there's our function v1. All right. So we've got v1, we've got v2. So finally, we're ready to plug them in. We had our form and we figured out what those functions are. So there's our v1 and there's our v2. So we're almost done. One of the things that you always want to do when you get to an answer is try and simplify it. So let's see if we can simplify this a little bit. If we distribute the cosine t, this cosine t sine t will cancel with that negative cosine t sine t. And what you'll be left with is just this last remaining term. And then, you know, it sure would be nice if we could get rid of those absolute values. Well, look, we're on the interval negative pi over 2 to pi over 2. Okay, so it turns out we can remove the absolute value bars. Here's why. Let me draw a unit circle for you. Negative pi over 2 to pi over 2 would be over on this side, right? What can you tell me about all of the cosine values on that side of the unit circle? They all have something. What's that?
Aren't they all going to be positive?
They're all positive. Yeah, so maybe that'll be useful. What about the sine values? What do they range between?
-1 to +1.
Yep, exactly. The sine values are the y values. So -1 to +1. And since we're not including the endpoints, we could say strictly between -1 and 1. So look what happens. You've got these absolute value bars on secant t plus tan t. We all know that we can remove absolute value bars if the thing inside is already positive. The bars aren't serving any purpose if it's already positive. So look, secant t plus tan t, we can write this way. We can combine this. They have the same denominator. And now look, on this interval, this guy is positive, right? Cosine t is positive on negative pi over 2 to pi over 2. Now, sine t is between -1 and 1, inclusive, or what's the word? Strictly between -1 and 1. But if we add 1 to it, now it's between 0 and 2, which is positive. So both the top and the bottom are positive on this interval. So what that means is secant t plus tan t is always positive in that interval, which means we can drop the absolute value bars so that we can write our particular solution this way. Okay, there's lots of this. I've mentioned this a couple times in previous lectures, but there's lots of this kind of math and small little things that you'll have to sort out in your head. A lot of it has to do with absolute value bars, which is frustrating sometimes, but you'll get a handle on them after a while. Okay, so we were after, let's see, the general solution, right? I think we have all the pieces. We have the homogeneous solution, and we have a particular solution there. So we just add them together, and you'll notice that we have, let's see, two constants right there and right there for the general, which seems reasonable, right? It's a second order differential equation. Okay, and then I promised I would tell you why the constants get absorbed. Well, if you included the constants, remember up here, these guys, C2 and where's the other one? And C1. If you include them, what ends up happening is they get pushed through to the Y1 and Y2, but those are already parts of the homogeneous solution over on the end here. Your Y1 and Y2. So what'll happen is, probably should have wrote a C1 and a C2 there. So what'll happen is you'll have this extra term flopped over right there after this guy, and then you just absorb them right into the homogeneous solution. And you just get new constants, but it's the same thing. All right, so that's one time through. Do you guys have any questions on that? So one of the things you'll want to do, I don't know if all of you are doing this, but please try and read through the notes ahead of time before we have our class meetings. Otherwise, it's really hard to follow people when they're showing you math. I don't know if you've realized that. I was helping a student today, and he was working on a problem I wasn't familiar with, and it was really hard to follow. So I can empathize with you. So what you want to do is read ahead of time, right? Become familiar with the problem so that you can walk through it with me. Otherwise, it's not really the most efficient use of time. So do your best, it'll help. All right, another example. We're going to find a particular solution, this time just a particular, which is what these methods allow for, to this guy. Now, can we directly use undetermined coefficients on that? It doesn't work, right? In order to use undetermined coefficients, it has to be polynomials, exponentials, sines or cosines, right? And even if we included the superposition principle, it works on this building block. It works on that building block, but it doesn't work on that building block. So it's not going to work on the whole thing. So we can't really use undetermined coefficients on the entire thing. But what we can do is we can use undetermined coefficients on this part, and we can use variation of parameters on this part. In fact, we already did this problem. This was example 1, right? So that's one of our building blocks, is our solution in example 1. You guys following? Okay. Now, this guy over here, you might think it's 2 building blocks, but it's actually just 1 building block. Remember, you're allowed to use polynomials. We extended power functions to include polynomials, and that's clearly a polynomial. So you don't have to break it apart if you don't want to. All right, so not much work to be done here because we've already done most of it. We do have to be a little careful, though. We already found the corresponding auxiliary equation, and we found the roots. So we had 2 roots, r equals I and r equals negative I. So we can't use undetermined coefficients. However, if we break it apart using the superposition principle, we have 2 things we can work on. This one using variation of parameters, which we already solved, and this one using undetermined coefficients, which is relatively easy. All right, so we already found this. I'll call this solution YP1. That's the one that we did in example 1. And this one, I think you guys can do. We've done a lot of these. You had a lot of homework on them. We'll call this solution YP2. So it ends up being 3t minus 1, surprisingly. Does that work? Yeah, that works. You plug it in. So so that's a particular solution. So you could actually find this one just by guess and checking. In any case, we do have to be a little careful here. Remember, with undetermined coefficients, you have to check for complications because you might have to add an extra factor of t. So what you want to do is identify either your R, alpha, and beta, either your R or your alpha and beta. So in this particular case, in this particular case, are we working with an R value or an alpha and beta problem? Do you see any cosines or sines? If you don't see cosines or sines, then you're going to use an R problem, right? So what does R equal here? 0. Remember, it's always on the exponential part. So there's a hidden 0 to the t there. So 0, that's what I'm using. Okay, so R equals 0, and R equals 0 does not match the roots of the auxiliary equation. So what that means is there's no complications to worry about in any case when we were solving for this. So in any case, by the superposition principle, we found our solution to this equation. We found our solution to this equation. So we can just add them together. We only need one of the tangent t's and one of the 3t minus 1s. So we only need one of each. So one of that one and one of that one. We just add them together. Is that okay? All right, so that's going to be probably the bulk of your homework. We will talk about the variable coefficients real quickly, but the variable coefficients are mainly going to be handled in the next section, 4.7, and then also handled in chapter 8, which is series. That's going to probably be the hardest section for the class.
Professor?
Yeah.
Let's say we did have a match. Would we have to add that extra value to both YP1 and YP2 or just YP2?
Let's see. That's a good question. So you do the undetermined coefficients. If you had a match, you just have to add it to this one right here. Just to that one. That's the only one.
Gotcha. Thank you.
Yep. Okay. All right. And finally, close this up. Variable coefficient equations. So this is kind of an add-on bonus for using variation of parameters. So it turns out that not only can this be any function, I'm kind of fibbing just a little bit. It can't be any function. It has to satisfy some integrability requirements because we do have to integrate, right? But it can certainly handle anything that we're going to work on in this class. All right, so you'll notice that we've now generalized even further. We've relaxed the conditions so that now the constants can also be variable. And yeah, our goal is to solve these guys. So here's the issue, though. It's a rather serious issue, at least from a mathematician's perspective. So we can use variation of parameters. That's perfectly fine. However, in order to use variation of parameters, you have to find a y1 and y2 solution that are linearly independent to the corresponding homogeneous equation. That's what you need in order to use the rule. The problem is we don't have a method for solving this equation. Sections 4.2 and 4.3 only apply when the coefficients are constants. And unfortunately, we're now in a situation where the coefficients are not constants. We have no real regular method for solving these, unfortunately. So at least not yet. We're going to use series later on. There is this one special case called a Cauchy-Euler equation. If these functions in front happen to be special, if there are certain functions, there's a way to kind of solve it without using series. And I'm going to show you that in the next section. But for now, really, there's nothing we can do, right? Because we need to find a y1 and y2 to the homogeneous equation. So there's not much we can do. So what is this next example going to be? Well, the only thing I can do is give them to you for free. Okay, just to show you how the process would work, assuming that we were able to find a y1 and y2. Okay, so that's what we're going to do. Here's a variable coefficient equation. First, make sure you can spot it. It's second order. It's linear. There's the non-homogeneity. The t squared is variable. The negative 4t is variable. And the 6 is not variable, but in general, it's a variable coefficient equation. So, okay, in order to solve these ones, you have to use variation of parameters, at least until we get to the Cauchy-Euler equations in the next section. Unfortunately, we need a y1 and y2, a solution, two linearly independent solutions to the corresponding homogeneous. So what do? We give them to you for free, at least in this section. Okay, so there they are. Those are definitely linearly independent, and they are solutions. You can check them if you want. All right, so this makes our work pretty easy. It's a straightforward application of variation of parameters. We're going to set up our system. We have our y1 and our y2. There's our y1, there's our y2. We're going to need the derivatives, so you can find those real quickly. We know what f is. F is over on the right. And we know what a is. That's the coefficient right there, which is the second degree term, which is t squared. All right, so then we write down our system, we plug everything in, and we've got this system. And we want to solve the same thing that we always do for variation of parameters, solve for v1 prime and v2 prime. Okay, you guys can solve this system. You're going to, I'm not going to show you here, but you guys can do it. Let's say you wanted to eliminate the v1 primes. What do you suggest we multiply the first equation by? I want to eliminate the v1 primes. Yeah, let's multiply the first equation by 2. All right, I'll even do that here. That's shorthand for multiplying the first equation by 2. What should I multiply the second equation by? Yeah, Michaela says negative t. Do you see why that's going to work? It's going to make the first terms, the v1 prime terms, it's going to make them opposites of each other. And then you can add them together. The v1 primes will be eliminated. And you'll have an equation in just v2 prime. Okay, so solving the system, you guys can do that. You're going to find your v1 prime and your v2 prime. Then you're going to use direct integration on each. You can somewhat ignore the constants, right? They don't matter. You're welcome to use them if you want to make the problem harder, but you don't need them, so choose zeros. And then you're going to plug those in. And you're going to simplify, and there's your particular solution. That solution, that is one solution to this differential equation. Could you guys find the general? You know how to do that? You have yp. How would you find yh here?
Homogeneous equation.
Yeah, you have all the pieces. You have two linearly independent solutions to the homogeneous equation. So you just add, just slap c's in front of both of these, add them together, and that's yh. So then you have yp and yh, add them together, and now you have the general. Is that okay? Also, you'll note that this equation only makes sense, we're saying on t greater than 0. The reason for that is you're going to have to break things up when t is equal to 0. If t is equal to 0, then we lose this second degree or second order term. So you have to pick a side, either t greater than 0 or t less than 0. So in all the problems we're going to work through, it's always t greater than 0. It makes the work a little easier, although it's very similar. Okay, let me stop recording here. We've ended early today. Awesome.